Hi everyone, so in this lesson we're going to go over the synapses, and in this lesson we'll review how action potentials and synapses interact to relay signals across multiple neurons. Just a heads up, the content we'll review is impulse versus synapse, the differences between the two. In addition to that, we're going to go over the anatomy of a synapse as well as how those synapses are regulated. In this lesson, we'll review these key vocabulary. However, just a heads up, the voltage-gated sodium channels, the voltage-gated calcium channels, and the neurotransmitter-containing vesicles and chemically gated sodium channels, those vocabulary are going to come up in the anatomy, and they're not going to be formal definitions, but what will be covered in the lesson that you should know with these key vocabulary words is how they work within the synapse when it comes to the anatomy and function of the synapse. Okay, so before we go over the difference between impulse and synapse, we need to know why synapses happen. So, just reviewing how neuron types interact, I'm just reminding you that neurons typically, there are three major classes of neurons, and they're not always used, but in all interactions between neurons, but they're often used. And in this case, what happens is our sensory neurons is the neurons that pick up information. They can be attached to external sensations or internal sensations in your body. And we want our sensory neurons to be there because what they do is they create a threshold and they don't create a response or reaction or sensation in your body unless the sensory neuron has had a strong enough signal or kind of pushing on it, something to trigger it very strongly. All right. So a good example of this is, for instance, you may not feel anything on your back right now, but actually you are because your clothes are gently brushing your back, and maybe now you're aware of your clothes gently brushing your back. But for the most part, you don't really sense it, you don't really notice it because your sensory neurons kind of learn to ignore the pressure sensation of the shirt on your back. Okay? However, once it does receive a strong enough signal, then it'll send an impulse down itself, and then that will lead to it interacting at or transferring that signal to either an interneuron or directly to a motor neuron. So if it goes to an interneuron, that interneuron will further process that information and potentially relay that one sensory neuron signal to multiple neurons in your body, multiple other areas of your body to coordinate many directional response from multiple places, or it may synapse directly with a motor neuron, which will create a simple reaction. But however that is, whether you go directly to the motor neuron from the sensory neuron or through interneurons, eventually that signal when reaching the motor neuron will help lead to some kind of effective response. So our sensory information comes in from our sensory neurons. It travels to our central nervous system, which often has interneurons take in the information and analyze, interpret it, and send it out. And then when it gets sent out, it goes into your motor neurons, which create an effective response by triggering or activating an effector muscle or effector gland. Now, that means that we're traveling through multiple neurons, which means we need to know how a signal gets moved across two neurons, and that's at the synapse. So just a reminder, and you've gotten this in the previous lesson, just reminding you, an impulse is that electrical current that's traveling along a neuron, and a synapse is the gap between two neurons, or maybe even a neuron and its effector organ or muscle or whatever. And the way the information is passed between the synapses or between the two neurons across the synapse is through a chemical called neurotransmitters, which are special chemical messengers. And there's different kinds of neurotransmitters that allow the neurons to talk to other tissues or other neurons. Okay, so in terms of communication between two neurons, though, formally speaking, there's two ways communication occurs: through electricity, the impulse, which is, again, that action potential down the neuron. So again, it's that action potential. Sometimes people call voltage. Sometimes people just say impulse. But ultimately, this is only for transmission of a signal across the one neuron. However, if I need to jump the gap and transmit between two neurons or a neuron and something else, then I'm going to use my neurotransmitter or my chemicals, which will then help diffuse across that gap and send out information. And again, those effector organ examples might be a muscle, it might be a gland that sends out hormones into your blood, which will then trigger a response from many other organs. There's many different ways that these signals can be moved around and these effects can be caused. All right, so this over here is a picture of kind of a fancy version of a synapse, right? So that whiting is the example of electricity impulse traveling down, and those dots that are going across, diffusing across, those are the neurotransmitters being released. All right, this is sort of a cartoony image of the synapse, and we're going to go through every single thing you see in this image step by step when we go over the anatomy of a synapse. All right, but there are some terms that are going to come up over and over again when we talk about the synapse and the different neurons interacting. So we already mentioned in prior lessons the synaptic cleft, which is a space that separates the two synapsing neurons. And typically we designate the neuron that is sending out information into the synaptic cleft the presynaptic neuron. That's the first neuron in the pathway that comes before the synapse, and it sends out neurotransmitters out when its axon terminal receives the impulse. Then the neuron over here that's receiving the neurotransmitters and initiating a response once it gets the neurotransmitters, that dude's the postsynaptic neuron. So that's the next neuron in the pathway that comes after the synapse. And the neurotransmitters then bind to the receptors found on this neuron's dendrites. And that's going to initiate an impulse that's, again, going to travel, have the action potential travel down the dendrite into the cell body. It gets processed and then passed along the axon and then down the neuron into whatever else it's going to go into. Another neuron, an effector, whatever else. But just a reminder, so the name presynaptic and postsynaptic neuron is relational to the synapse you're studying at any given moment. So let's say we're looking at this synapse over here between neuron 1 and neuron 2. Well, in that case, neuron 1 is the presynaptic neuron because it's the signal's going in this direction from dendrite to axon, then dendrite to axon. So this is the presynaptic neuron, and this is a postsynaptic neuron. However, if I'm looking at this synapse over here, and again, my signal is going down this way, then neuron 2 is the presynaptic neuron for this synapse, and this neuron over here is the postsynaptic neuron. So it's relational to whatever synapse you're looking at. So neuron 2, its dendrite end here makes it the postsynaptic neuron, but if I'm looking at this synapse here, its axon end, when we're looking at it in relationship to this synapse, makes it the presynaptic neuron, okay? Presynaptic sends out the neurotransmitter, postsynaptic takes in the information from the neurotransmitters to create a new response in that one axon. Okay, so this is a close-up of the synapse found between the presynaptic neuron and the postsynaptic neuron, with the impulse being traveling along the presynaptic neuron and then jumping across the synapse over here before traveling down the postsynaptic neuron. But this is what we're going to draw out, and then we're going to add to it. It's sort of a close-up view of what I want you to draw out. And then on the next slide, I'll draw kind of like the simplest form I can of this. For those of you who aren't drawers, this is how I do it, but I do it with something erasable. So I draw out kind of the outline on top of the presynaptic neuron, then I erase the elements where I'm going to draw channels. So I have that so far. Now I'm going to add my vesicle. So this is a vesicle leaving, and I'm going to draw on some vesicles inside. The green dots are neurotransmitters, stuff like that. Okay, so we have this first drawing of a neuron, then I'm going to do the second drawing of the neuron. So we're going to label this presynaptic neuron. So again, we want to kind of draw something erasable, and then we'll come in, and we'll just kind of erase sections to add gates. So this is going to be my postsynaptic neuron. I'm adding gates to the bottom. This is actually the same type of gate as drawn on the top one, called a voltage-gated sodium channel. So I'm just drawing it out. The gates on the top of the postsynaptic neuron is a little bit unique because it needs to have like kind of a dip inside of it so it can bind to chemicals. So I'm going to draw it like that. Alright, so some major things. This middle section is what we call the synaptic cleft. This is the axon of the synaptic neuron, or the axon terminal more specifically. And for the postsynaptic cleft, this is actually part of the dendrites. So just a heads up. So I'm going to kind of walk you through what's happening in each of these images. And then after this, I have some nicer picture versions of this when it's not sketched awfully on the iPad. So here's what happens. First, we have our electrical impulse, our action potential, traveling down the axon of my presynaptic neuron. This electrical impulse is going to open my voltage-gated sodium channels, which, just like any other part of the action potential, once it's open, is going to allow sodium to flood inside. Alright, so I drew that out so it's a little clearer. Sodium's coming inside. Alright, because that sodium's coming inside, that's going to make the very edge of my axon positive, which is then going to trigger the very end of the axon terminal, which has voltage-gated channels for calcium to open. And when those swing open, they're going to allow calcium to come in, but not just anywhere. That calcium is going to bind to these purple things. These purple things are vesicles with neurotransmitters. So when those vesicles get bound with calcium, that's going to induce the vesicles to fuse through exocytosis with the very end of the axon terminal and then dump the neurotransmitters inside of it into the synaptic cleft, the gap inside the synapse. So all the vesicles are going to start dumping neurotransmitters. That's going to allow the neurotransmitters time to diffuse across the synaptic cleft, and then when it binds to one of the channels on the opposite side, and these channels are binding the neurotransmitters, so they're opening based on the binding of a chemical molecule, not electricity, not voltage, that's going to cause this channel to swing open and allow, this time, sodium on the outside to travel through. So this is a sodium channel, but it's not voltage gated, it's chemically gated. It opens based on that chemical. Sometimes people call this chemical a ligand. And just like an action potential, that's going to make the inside a little bit more positive, which is then going to start inducing a action potential on the second neuron, because that charge change is going to open up, just like an action potential. It's going to open up the next part of the neuron's channels, and it's going to do it through a charge chain, which means it's going to open up another voltage-gated channel for sodium, just like above with our action potential, as it leads down the neuron into another impulse for action potential. Okay? So basically, our vesicles powered through the calcium, the voltage-gated calcium channels, are what allow the neurotransmitters to jump from one neuron to the next. But ultimately, it's just going to lead to a second impulse to continue the electrical flow across this large neuron before it hits a next neuron that has to jump or whatever else it needs to do. Sometimes, instead of another neuron, after this section here, what happens is the neurotransmitters may, instead of touching another neuron, it may bind to a muscle. cell, or it might bind to a gland and then trigger a response in that effector organ. But that's basically the idea. We get to the very end of our neuron, then the calcium-gated channels open and help release the neurotransmitters, and those neurotransmitters will then induce a response on the next thing. In the case of a neuron, it just starts another impulse. In the case of an effector cell, it can cause the muscle to contract. It can cause the gland to release a hormone, whatever you need. All right, so these images are just less terrible versions of the pictures I just drew out, so it's a little bit clearer. All right, but what I'm going to do is we're going to write out the steps that we just kind of covered, but in a way that you have it all nice and neatly written out for you. So how do the signals cross the synapse? So step 1, we got our action potential that's inducing those voltage-gated sodium channels to open up like any other action potential. But they're about to hit the end of the axon, at the axon terminal of the presynaptic neuron. And that's going to kickstart step 2, the calcium channels opening, voltage-gated calcium channels opening, which allow them to bind the neurotransmitters, which is going to then trigger step 3, the release of neurotransmitters into the synaptic cleft. That's going to give time for the neurotransmitters to bind and diffuse and bind into the chemically gated sodium channels on the other neuron, the postsynaptic neuron, over here. And that's going to open up and allow sodium to come in to make it more positive. And that's going to cause a new impulse to start on the next channel where more sodium can come in. Okay? And I just realized I forgot to draw off step 5 on the last image, so just real quick, we should add the step 5 with sodium coming in. Okay. So anyways, these images show you how that animation of the synapse movement works. So over here we have our action potential. Okay, I'll play it again. We have our action potential reach the end of our presynaptic neuron. You can't really see it, they don't zoom in, but basically that's going to trigger calcium to go cause a neurotransmitter to be released from the vesicles into the synaptic cleft, and that's going to cross and bind these channels over here, these chemically gated channels that's then going to allow sodium to get in. The video or the GIF below will show you kind of what that looks like. If you zoom in over here, what it kind of looks like, all right? So in this case, the yellow is the neurotransmitters, and these purple things over here are the chemically gated sodium channels. So you can see the synaptic cleft is receiving the neurotransmitters. It diffuses across, binds the gates across, and those gates now open, and it's going to allow sodium to flow in, and that's going to change the charge on this end of the dendrite of our postsynaptic neuron, which is then going to trigger that new impulse to occur in the voltage-gated channels. All right, so this is another image of a synapse diagram. The difference between this diagram and the ones I drew for you is it lacks detail on how the action potential arrives and is regenerated on the postsynaptic neuron. So just a heads up. But I like this. It's another way of viewing the action potential. And this one is another way of viewing the way the action potential interacts with the synaptic cleft. And in fact, what ends up happening is if you zoom in on the chemically gated ion channels on the opposite side, it works really similar to the sodium-potassium pump used in action potential impulses, except it requires a neurotransmitter to get that pump to actually turn on. All right, so let's go over regulating the synapse. So you want to regulate the synapse and remove the neurotransmitters in the synaptic cleft after they're released and after they've already stimulated the response in the postsynaptic neuron. So there's 3 ways you can remove the neurotransmitters. One, you can wait for them to diffuse out. It'll take a little bit longer, but this is a good way to allow the neurotransmitters to leave without putting in a lot of effort, and it can be used in responses where it's not important to turn off the second neuron, the postsynaptic neuron, immediately. Maybe you'll use this for dopamine, which helps regulate mood. Maybe you'll use this for the production of a um, hormone that's kind of like more mellow. It doesn't create like a really quick response, such as long-term estrogen production during puberty. Okay? However, if the response you're doing is very fine and you need it to be produced and then to be removed very quickly, then you're going to want to do something else. And in this case, what you'll want to do is get rid of the neurotransmitters ASAP. So one of that ways is you can destroy it with enzymes, but that has a downside because when you destroy the neurotransmitters that are released, it's going to take longer for the presynaptic neuron to regenerate enough neurotransmitters to create a response. So it'll create a lag time before this neuron can be used again. Or this is useful for neurons that you might want to fire constantly, meaning it just zap, 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 like repeatedly releasing stuff. Then what you want to do is maybe do something called reuptake. So in this case, any neurotransmitters released then get reuptaken or vacuumed in, sucked back in, going through endocytosis, but it's basically retaken into the presynaptic neuron to be recycled for future signals. So if you have a neuron that's going to fire multiple times, then reuptake is a better bet. But ultimately, all these things are ways to allow controlling of your neuron response, because it allows more fine-tuning in your body. Sometimes the strength of the response in your body is based on how often the neuron is fired. So neurons, when they fire once, they don't have they don't have a dial. They don't have like a level 10 and a level 1 volume when it comes to the strength of a neuron's response. What they do have is you can control the strength of your response based on how often your neurons get fire and produce an impulse. So maybe, for example, in a pain neuron, a nociceptor neuron, what happens is a really soft pain, like being a light bruising, that might turn on your pain receptor a couple times, but getting stabbed or punched might turn on your pain receptors 1,000 times over and turn on that neuron impulse and create thousands of impulses really quickly. Okay, so that's fine-tuning control. That's allowing your neurons to have more control and more variation in how strong the response can be. All right. So if you don't remove the neurotransmitters, the neuron will keep firing. Maybe that's something you want, but maybe it's not. Maybe you only want to move your arm once to get away from the object, but not like 1,000 times, at which point you'll have like possible muscle damage or weird spastic movements. Okay, so it turns out that a lot of drugs, a lot of conventional pharmaceuticals interfere with the synapse and interfere with the neurotransmitters at the synapse. And what happens, one of the examples, is you can prevent the removal of a neurotransmitter to strengthen the neurotransmitter signal. So Prozac is a classic example of that. So in this case, SSRI Prozac is just a kind of SSRI. SSRI is a very common medication used in depression. So it stands for selective serotonin reuptake inhibition. So serotonin is a neurotransmitter related to mood and sleep and memory. If you're depressed, some people, when they're depressed, it's due to a low amount of serotonin being produced. So if you prevent uptake of the serotonin, if you prevent removal of the serotonin, any serotonin that's released into the synapse has more opportunity to re-trigger and re-stimulate the postsynaptic neuron to produce more responses, more impulses that on your neurons that are related to serotonin, related to mood. Okay? So it has a chance to prolong and strengthen its effects. In this case, produce more relaxation. So this is just the same information, but I wanted to show this image of what's happening. So this section would normally vacuum out the serotonin, but instead it's being blocked off by the medication, and any serotonin in the synapse is now going to just keep rebinding the postsynaptic neuron to keep triggering the serotonin response. You can also do the opposite. You can have drugs that prevent the release of neurotransmitters into the synapse. It all depends on the drug and its effects when it's studied in people. All right. Another way you can regulate the synapse is, instead of regulating the synapse itself, you can regulate the action impulse. Because remember, our impulse is what eventually leads to our synapse and the release of the neurotransmitters. So, going back to this slide over here, one way to interfere with the synapse is to prevent the signal from even reaching the synapse, meaning blocking the action potential. So a classic example of that happening is local anesthetics. So lidocaine and novocaine, they actually interfere with the root of all action potentials, meaning they stop voltage-gated sodium channels from working. Now this, on the other hand, is a very dangerous drug to have throughout your body because all the neurons in your body function using action potentials. So if you took lidocaine or novocaine and put it in your blood and pumped a ton of it into your blood, you'd basically shut down your neurons. And then your body would stop working. So this is why lidocaine and novocaine is injected directly next to whatever you're trying to numb, and in small amounts. So when a dentist injects novocaine, they're going to inject it right next to the tooth that they're working on. You'll also notice, in addition to blocking pain, it's going to numb movement in that area, and that's because it stops neurons from working. So the neurons nearby whatever you're doing surgery on, oral surgery on, hey, it doesn't distinguish between pain sensing or motor movement. They're just going to stop. Okay? But it must be local so you don't interfere with, critical to life neurons. Okay, so key takeaways. So when we use multiple neurons, we need a way to transmit signals across the gap, and we're going to do that with chemical neurotransmitters. So that's the process of converting the action potential across the axon terminal with chemicals, and it's done first when the action potential reaches the end and voltage-gated channels that allow calcium in bind to the neurotransmitters and release them into the cleft. At that point, when the neurotransmitters are released into the cleft, they'll bind chemically gated channels on the other neuron, and then that will start a new impulse. We need to remove those neurotransmitters immediately afterwards to provide a little bit more control, and drugs can interfere with that removal or release of neurotransmitters. So a lot of drugs work within the synaptic cleft. All right, so that concludes the lesson. Move on to any other work.